Good morning, everyone, both in person and on Zoom, where I know there are a couple people at least on Zoom as well. My name is Bruce Momjian. I am one of the Postgres core team members and have been an Enterprise DB employee for 15 years. So it's my 15-year anniversary, yay. This is only my second in-person conference since COVID started. I used to do a lot of them. Now they're all virtual mostly, but again, it's exciting that we have an in-person conference here in Raleigh today. I've been asked today to talk about securing Postgres from external attack. It is a very interesting talk because, of course, a database is a very complicated piece of software, and figuring out kind of how to make it secure is not a simple turn on one switch or configure one thing. It's sort of a holistic process that you have to go through. And I'm going to explain some of the details of it. And hopefully you're going to come out of it with a little better understanding of how to secure your Postgres database. We're going to talk about attack vectors. So effectively, we're going to be speaking about how someone could attack you and then how you effectively defend against those attacks. What we are not going to be talking about today, which could be the topic of another talk, is external attack. I'm sorry, what we're going to be talking about today is external attack vectors, effectively things that happen from outside the permission system of the database coming in. So how you configure your your security, how you set your passwords, the idea of authentication theft, the idea of snooping, pass-through spoofing. I'll talk about those things. You may not have heard those terms before, but they're actually very important. And then finally, we'll talk about some sort of meta topics, things like backup theft and administrator access. What we are not going to cover, as I said, are internal attacks. So attacks from people who are already in the database and therefore extend their permissions. This could be related to setting up object permissions or SQL injection or application vulnerability. We're not going to be covering this, and that could be another talk. So let's talk about authentication security. This is probably the most straightforward method to basically secure Postgres. We have a file as part of Postgres, which is called the pg_hba.conf file. HBA stands for host-based authentication. This file was developed very early on in the Postgres code base, and it effectively gives you a way of controlling access to the database. Now, the nice thing about it is it's very comprehensive. You have the first column, which is your type of connection, but then we have the ability to control on the database level, on the user level, on the IP address level, and then at the end, we specify how are we going to authenticate people. Now, if you're installing Postgres from source code, the default authentication method for practical reasons is trust. And this is probably your first red flag in terms of security. If you trust everyone on that local machine, then that's fine. And if you're running on a laptop, again, you're not talking about people coming from outside the network into your laptop. That would not be allowed. Postgres would prevent that because you can see the way the IP addresses are set up. You can only do it from inside. But if you trust everyone on your machine, then that's a great default. But in most cases, that's not a great default, particularly for a production workload. So there is a special flag when you initialize your database, -A, which allows you to change the authentication method. Now, we support a whole bunch of different authentication methods. We basically have to support whatever authentication method that is supported in your enterprise, whether it's LDAP or PAM or Kerberos or Radius. I mean, there's a whole bunch of them that we have. You can pick the one that kind of meets your needs. We even have an SSL certificate authentication, which I think is really cool. But again, that's your first place is to look in this HBA file to look at how are we allowing network connections into our system, and where do we want to kind of like control that. Okay, so that's kind of the first piece you want to look at. Now, let's suppose that you pick password. Now, password is not really recommended for a lot of people, but there are some people who do use it. It does kind of make a little sense if you're using SSL connections, but we'll get into that in a minute. I wanted to highlight password as an authentication method because there is a very clear way that you can see how the password would be a problem. This is why we don't recommend the password. What happens in this diagram, as you can see, is the database client makes a connection request right here. And effectively, the database comes back and says, I need a password, and the client just sends the password across. Now, that's obviously a problem because effectively the password has now been sent across the network in plain text, so anyone who's on your network who can see network traffic would be able to kind of use that password later. So that obviously is not a great method. Now, as you can see on the right here, we do store the passwords in the database in either MD5 format or a later format that's more modern called SCRAM. We're going to talk about that a little later, but that doesn't really help us because the password has gone across the network without any kind of protection. Now, we're going to talk about SSL, or TLS is the more modern name for that. And that does give you some protection, but it's not sufficient, and I'm going to explain that. Again, this is a hard talk because I'd love to just say do X and then and you don't have to worry about anything anymore. But as you're going to see through this talk, I'm going to show you X, I'm going to show you what's wrong with X, and then I'm going to show you Y, and then I'm going to show what's wrong with Y, and then kind of work our way out to what is considered to be the industry best practice for security. All right, and that's really why I developed this talk, to give you that whole panorama of what is insufficient, why is it insufficient, and then what do we need to do to make it sufficient. So let's suppose we don't use the password method, it's called password, and we use something called MD5. Now MD5 is an older version. Again, as I said before, we have a new SCRAM method that I'll be talking about later, but let's just use MD5 just for an example. So the client sends a connection request across. The server sends back, it says, I need MD5, and then it sends something called a random salt. I don't know how many of you know what the salt feature does for encryption, but it effectively adds some randomness to the password. So when the client sends back the response, it doesn't send back the raw password. It encrypts it with MD5 and adds the salt into that response, okay? Now you might say, well, why would it do that? What is the salt giving me? Well, that random salt is going to be different for every connection, okay? So if I have a connection here at the top that uses salt 0, okay, and it sends salt 0 to the client, and the client sends back the reply double encrypted with MD5 and uses salt 0. Then a malicious attacker, in this case the bottom one, could send a connection request, and the reply from the database would not be salt 0. Remember, it's random, so now it's salt 1. And if the malicious attacker has seen the salt 0 go back and it just replies with the salt 0, they will not be allowed access, because the server says, I sent you salt 1, I want to get a reply back with the valid password mixed into the MD5 with salt 0. But it was salt 1 because I sent you salt 1. If you send me salt 0 back, it's not going to match. Okay. Now you might think, well, this is great. Our problems are solved. We don't have to worry anymore. Okay. The problem, and this MD5 method was developed by me and a bunch of other people back in the early 2000s, and it lasted for quite a while as sort of considered secure, but the salt, unfortunately, is only 4 bytes. And if you're familiar with the birthday problem and the problem of preventing duplication effectively, when you have a 4-byte integer, you can almost guarantee that the salt will be repeated after about 64,000 connection requests. So you could keep connecting over and over again until you get salt 0. Right now, 64,000 connection requests is going to take a while, but it's a finite amount of time. And if you want to get in, you obviously may be able to get in. Now, somebody might notice that many failed connection requests, but it's far from foolproof. I mean, in hindsight, if we had used a 8-byte salt at that time, that would have made a lot of sense. At the time we were developing this, 8-byte integers weren't even universally supported on most operating systems. So again, we're going pretty far back here. And as I'm going to show you later, there are better solutions that I'm going to show you that have more modern solutions to this problem. Okay. Any questions so far? I love to take questions. I don't think we're going to be able to get questions from the Zoom audience, but if anybody had a question, okay, we'll keep going. Thank you. As I said before, starting in Postgres 10, which was 5 years ago, we introduced a new authentication method called SCRAM. And as you can see from the full name of the authentication method is SCRAM-SHA-256. So there's two things you learn from this. One, instead of using MD5, which is not a great cipher in not a great hash method in modern computing, SHA-256 is a much more robust, obviously a much longer and hard to guess hash method. Now, it doesn't mean there really is anything wrong with MD5. The way we use it is quite safe, but SHA-256 is certainly a much more modern and robust hash method. The second part you can see from the SCRAM SHA-256 is the word SCRAM. And effectively what SCRAM is it's basically taking that MD5 method that I showed you with the random salt and sending it across and back again and bringing a modern infrastructure to that. So it's really the same concept, except that there is a SCRAM specification. IETF has a specification for SCRAM, and we follow that specification. So any client-server protocol that's using SCRAM is using the same API, the same methods. And of course, these methods and this specification has been gone over by cryptographers and security experts. So it's a much better, more standard way of preventing that password from really kind of being used. There's another SCRAM method which is available in Postgres 13, which also allows authentication of the server, and I'm going to get into that in a minute. Very similar to the way you do certificate authentication, and then in Postgres 14, which came out a couple weeks ago, now this SCRAM-256 is now the default for storing passwords, because up until Postgres 14, the default was still MD5. So again, this is sort of a modernization. It took us sort of 5 years. In fact, the reason it took us 5 years is we had to wait for all supported clients to understand SCRAM before we could then change the default password storage method. So if you have Postgres 9.6 or earlier clients, they might have trouble with passwords stored as SCRAM on the server. And again, that's why you have that 5-year gap in changing that. I'm going to be talking about channel mining a little later. Like here's an example of the SCRAM authentication. Looks very similar to the MD5, but it has a little more to it. As you can see at the top here, connection request goes in. Server says, I want SCRAM-SHA-256. The client sends its username and then something called a nonce. And a nonce is effectively just like a salt. It's a random number that we hope it doesn't repeat, but of course it's more than 4 bytes. Yay. You don't have the problem with repeating. Then the server sends back the client nonce, which is what it just received, and then it adds a server nonce to that. So now the client has picked a random number, the server has picked a random number, and then we have a salt on top of that. And then the client and server basically send a client nonce and server nonce, and then a proof, which kind of pulls all these numbers together, okay? And as you can see on the right-hand side, we're storing things now instead of MD5 as SHA-256, right? So again, if you're thinking about how do you send passwords back and forth in a secure way, SHA-256 with SCRAM is really the modern method, and I'm excited that we now offer that, okay? And again, Wikipedia here, article at the bottom, there's a little URL that kind of explains it. Although I don't see the URL there. Does anyone see it there? I should have showed you all the way at the beginning, and I'll do it now. Sorry. There we go. Just go back to the beginning. If you want the slides to this, right here is all the slides. So if you're interested in getting the slides or the URL I just showed you, feel free to do that. It's right there. So if you want the QR code or whatever, there are 56 presentations on that website, mostly related to Postgres, 97 recordings. I'd be curious if anyone uses the QR code. But again, it's momjian.us if you want the slides or any of the links that I show you here. So yeah, that's not their fault. It's just the black, the way the setting is. Oh, actually, I see a little bit of it now. So they actually improved it. You can see a little bit of the URL there. Great. What is our job done here, right? Is our job of passwords done? No, not really. One thing that Postgres does not support internally are checking for weak passwords, are checking for password reuse, or brute force password attacks, which is a serious problem. Unfortunately, none of these are prevented by Postgres directly. And normally, we recommend that you use if you want to protect for these things, we recommend you use an external tool that's designed to do that. Typically, LDAP, PAM, or SSPI are sort of the traditional ways that you prevent those type of attacks. You know, you're seeing less and less use of passwords, but I'm just trying to be complete and show you kind of what the attacks, possible attacks are in this particular case. Okay. So is our job done? Do we have no more problems? No. Even if we protect the passwords, we still have potentially queries going across the network and results coming back all the time. Okay, so maybe you can do the password, but effectively you still got these queries bouncing back and forth. And this obviously is vulnerable to snooping. So, you know, people can see that if somebody changes the password via SQL, right? That's going to be visible, right? Because you're sending it across the network, right? So again, another potential problem with the passwords is that you don't have a way of controlling that. So you look at that slide and you're like, well, okay, yeah, protect the passwords, but now it's the traffic that's a problem. So to the rescue, SSL, right? I mean, everyone's, you know, everyone kind of understands this is the direction you want to go in. People are familiar with this when using HTTPS on a website. You know, that's a secure socket layer or TLS layer on top of websites. And now all of the queries are encrypted using a password, a shared secret between the client and the server. There's something called a Diffie-Hellman protocol to negotiate a shared secret between two network devices, and it typically, TLS SSL typically uses that. And now all of my data is encrypted, and all of my queries are encrypted, my results are encrypted, and my job is done. I can go home and not worry about anything. But if you've been in this talk long enough, you probably realize that's also not true. Because there's this person, This is, instead of somebody snooping, namely looking at your data, there also can be people who spoof. And a spoofer versus a snooper is somebody who pretends to be someone else. And you might say, well, why is it important? Why would somebody want to pretend to be someone else? Well, let's look at the most simple case, and I'm going to give you a more complicated case in a minute. Let's suppose that your database server is shut down. It's not running. Maybe you're under maintenance. I don't know. And a database client tries to connect to Postgres. Well, Postgres listens typically on port 5432, or 5431, 5444, whatever. Some what we call unprivileged TCP/IP port. All of the port numbers above 1024, 1023 are non-privileged, meaning that any user on the system can start a service on that port. Right? Everything below that is root only, but anything above that is, and Postgres does not run as root. So it's always going to be 1024 or above, right? So what if I'm a bad actor and I know the database server's down? I'm going to just start up a process and I'm going to listen for connections on 5432. That's interesting. A database client says, I want to connect, and the server says, I need a password. I don't want to do SSH. I just want a password. Or maybe I want to do SSH, right? And the password's sent, and the database says, oh, no, sorry, it didn't work, or you mistyped it, or whatever, and it just goes away. Okay, well, effectively, that malicious server has now captured a password. And when the server starts up again, that password is going to work just fine. So that is a very simple case of somebody spoofing the database server, pretending to be the database server, and therefore capturing passwords that can be used at some point later. Now you might say, this is a contrived example. It's not going to happen in my case, okay? This is the case of having it. So this is the case where it sends the password. This is the case where it just basically sends it to the fake server and it records all the passwords that happen later. So you might say, okay, that's not something I care about. What about this? Okay, in this case, the database server is running just fine. Okay, on the right-hand side, database server, it's going great. Okay, but you've got this spoofer in the middle. It might be a large network. You can kind of fake your MAC address and maybe your IP address, depending on how the network's set up. And you effectively become a fake server. So the client sends a connection request to the fake server sends it to the real database. That's interesting. Then the reply comes back from the real database, and the fake database sends the request to the client. And it might modify the type of request. It might say, I need a plain password, and then it sends the password, and the password goes back to the database. And all of a sudden, that fake server has seen the password because it passed right through, right? And then all the queries go through the fake server and then come back through the fake server and go. So the real client has no idea that everything it does is being recorded. And in fact, the fake server can inject its own queries if it wants to, right? Because it's really authenticated using the client that it connected to. So this is a bad thing, right? This is not something you want. So you say, oh, okay, well, I'm going to bring SSL in, and SSL is going to take care of my problems. Maybe, okay? So the default method for clients is something called SSL prefer. There's a connection string where you specify the type of validation you want. And you say, I prefer certificates, okay, from the client. So the client says, I prefer certificates. A fake server says, we haven't even gotten the certificates yet. Client says, I prefer SSL. And the fake server says, I don't have SSL. And then the client says, okay, we'll just keep going without it. And then so we're back to where we were on the previous slide, right? And then maybe the client can say, I require SSL, right? I'm going to be, right? I'm going to require it. And the fake server says, okay, fine. We'll communicate via SSL, and I'll even communicate to the real server via SSL. No problem, right? Because I'm going to be able to read everything that comes through in my fake server. I'm just going to pass it along. So I can do SSL, no problem. I'm happy to do it. I'll be happy to read all the queries and all the results, and even I can add some if I want to, right? That's still a problem, right? We really haven't, we've got the connection between the two machines secure, but we don't know that the server, the endpoint we're talking to is really the server. Okay, and this is why SSL alone is rarely sufficient. So the real way to fix this and to get a robust solution is to use something called SSL certificates or TLS certificates. You've probably dealt with these a little bit, maybe when you've set up a server. A lot of people have what are called snake oil certificates, if you've ever heard of that term before. And what a certificate does is to basically prove that you are a specific machine. The way it normally works, and I have several blog entries about it if you're curious. My website has about 650 blog entries, but there's a bunch of them about certificates. And effectively, what a certificate does is you have a certificate on the client right here, which is signed by usually an enterprise-wide certificate authority. And then you have a certificate on the server, which is again signed by that certificate authority. And when the client has a special setting saying, I want to verify the certificate authority, the CA, okay, then it will basically, when it connects to the fake server must provide not only a valid certificate that was signed by the same certificate authority, but must prove that it knows the secret key that goes with that certificate. Certificates themselves are public. You can see certificates from any website you go to. Okay, if you just pull up in the menu from the browser, you can see the certificate. What you can't see is the private key that goes with that certificate. That's really where the proof is. So if you use SSL and you require clients to verify the CA, okay, then effectively, if they try and connect to a fake server using SSL, if that fake server is not able to provide a certificate and prove that it has the private key associated with it, the client will not connect to it. And that's really the only way, I think, to securely use SSL. The downside is that you have to set up certificates. You have to create a certificate authority within your organization. You have to install these certificates on the server. You have to install them on the client. And you potentially have to rotate these certificates. I do have documentation I did blog entries about this. We have, in the past couple of years, greatly improved the Postgres documentation, which explains exactly how to create a self-signed certificate as a certificate authority and how to use that certificate to sign other certificates that can then be placed on the client and on the server, which gives you that identity verification, which is really, I think, the only way, or probably in some ways the best way to use SSL. Okay. There is one, you notice I hedged a little bit. There is one other really interesting way to validate the identity of something, of the endpoint, particularly of the server, without using certificates. And that is something called channel binding. Now, channel binding was introduced, I believe, in Postgres 13 or 12. It's been around for a couple of years. But it only was enabled in libpq, I believe, in 13. And effectively what it does is it allows the password negotiation. It forces the server to prove that it knows the password, all right, without having to use certificates. So effectively, if you're using SSL, and then the server comes back and says, we're going to use SCRAM, and if the client has channel binding set up, then effectively what happens is that the database server will use its certificate, although it doesn't have to be a signed certificate technically. It will use a certificate and say it will mix the certificate with the password. So like it hashes the certificate, it combines the password with it, it hashes that together, and it sends it back, and it proves that the endpoint, which has a certificate, maybe signed, maybe not, okay, maybe self-signed, but it proves that the person on the other end, not only with has a certificate, also knows the password. And if that comes back from the server, as you can notice, it basically says channel binding required username, and it sends back that special value that effectively proves here that the server proves that I know the password that you're trying to log into, okay? And by doing that, you've authenticated that server without having to use certificates. So honestly, there's really only two ways to authenticate. It's either with certificate authority validation or technically with channel binding. In any other case, you're kind of open, I believe, to that spoofing problem, okay? Another cool way of doing authentication is SSL certificates. You can actually use the certificate on the client, again, usually signed by the same certificate authority, and you basically request, the server requests a certificate, and the client sends back a certificate with the same common name matching the username. And that's how you, instead of typing a password, you're effectively sending a certificate, and then you're sending proof that you know the password of that certificate together. And that authenticates you. So it kind of allows you to avoid passwords completely. You can do some cool things with this. For example, several certificates can be valid at the same time, right? Usually with a password, there's one password. As soon as you change it, everyone has to use the new password, right? It's like a cut in time. You know, password A, password B. You use password A as long as you can, and then all of a sudden everything has to start using password B. If you're using certificate authentication, I have a blog entry about this, you can effectively phase in new certificate authentication because the certificates have an expired date, right? So you could say a month before, I'm going to start installing new certificates on all my clients. And by the time at the end of the month, when they all expire, I will have updated them all. Very hard to do with passwords, but very easy to do with certificates. Any questions about that? I know I threw a lot at you, and usually you don't hear about these things, but you know, there's sort of this magic sauce that you get when you use a browser because it has HTTPS built into it, and it has a whole certificate store of all of the global or high-level certificate authentication agencies, including VeriSign and Let's Encrypt and all those big certificate authority. What were the other one? Trust Cert. Anyway, there's a whole bunch of them, and they're all in your browser. And if you look in your browser in the right place, you can actually see all of the stored certificates. And those are all the certificate authorities. They're used for all of the websites that you go to, and they all verify that when you go to a bank, when you go to anything with HTTPS, that endpoint has got to match the host name and has to be signed by a certificate authority in a chain that's in your browser. But when you have a database, you don't have a certificate store. It doesn't come with a certificate store. In fact, there's no value to that because you don't want to have a public certificate controlling who can access your database. You want to create your own certificate within your organization and then sign certificates where it makes sense. And that's effectively the process that happens. But on this downside, you have to set it up yourself. The good news is the Postgres docs are very clear. They've been updated in the past couple of years, and it very clearly shows you the commands you need to run to create a certificate authority, to sign multiple certificates, and to install those. on your clients and your servers. Any questions? Yes, sir. So is there any performance hit using channel binding? Not really. The TLS overhead is probably going to be much more significant because this, as I said earlier, even before you can send your first byte, it has to exchange a bunch of messages to do the Diffie-Hellman shared secret negotiation. And then once that starts, then you do have a couple more round trips just to send the packets back and forth. But other than that, yeah, I would not think there's any. The channel binding itself is just one extra packet, right? As you can see, the server sends back that proof that not only do I accept your password, but I know the password, right? Which the fake server would not. And it obviously doesn't send the literal password. It sends it hashed with its own certificate and its own private key, so that a fake server who would be able to see the real server certificate can't see its private key, can't create that special packet. And effectively, even if somebody was trying to replay that, it wouldn't work. Yeah, so because you're creating if you saw in the negotiation, client has a nonce, server has a nonce, those got to be the same to replay, and then you've got this salt in there, and then you've got to know so that's never going to replay, right? And that's nice. The nice thing using SCRAM and channel binding as a standard, because everyone understands how secure it is, and people have gone over it instead of what we did with NB5, where nothing really existed at that time. We just kind of created something ourselves, and in hindsight, we used a salt that was too small. And that, is disappointing, but it lasted for as long as we could use it. Other questions? Great. So as I said before, I wanted to go over that whole process of this is great, but this is great, but to get you to the point of understanding, why do we have to do so many things? Why do we need SSL? Why do we need to create certificates for these? Why do we effectively need a certificate authority? And it's really because the types of attacks, whether it's spoofing or snooping or setting up fake servers, all kind of require this to get a system that's secure from external attack. But there are some other things that effectively could impact your security, and I want to go over those in the final section here. The first one is disk volume encryption. Now, that might seem to be an odd thing to talk about for databases, but effectively, occasionally, media can be stolen. You may have a case where somebody pulls a disk drive out of a server. It might be somebody who pulls up, who leaves it with a backup tape. I was in a facility in the 90s, and I was in a server room, and there was this box of backup tapes in the corner of the server room, and I'm like, Herb, why is there a box of backup tapes here? Like why is it in the server room, right? It's tapes. He's like, well, he said, if somebody picks up a tape and they walk out of the building with it, they got all the data of the entire law firm. I'm like, oh, yeah, that's a good point, right? So what I learned from that is that physical media and backup media is obviously a very potent way of having your data leak out unintentionally. So it's really something that should be considered. A lot of people are not using or have secure server rooms, so that's usually not a problem. But also you need to think of the backup because some people store offsite backups, and you need to make sure those are secure as well, whether encrypted or kept in a box in a safe somehow. They do need to be kept secure. The second aspect, and this is something people might have thought of, is the idea of doing column encryption. So there's a number of cases where people are wanting to encrypt some of their data, perhaps for PCI compliance, where they have a particular column that they want to encrypt. And Postgres has very robust capabilities to do this type of encryption. There's something called PG Crypto, which has a very a sophisticated way of doing this encryption. I've written a tool called PG Crypto Key, which allows you to sort of negotiate a secret between the client and the server, so you don't have to pass a password inside a query string. If that's helpful to anybody, again, it's mentioned on in my blogs. But that kind of idea of column encryption, so that even if somebody was to steal or look at the data, there'd be certain columns that would be incomprehensible to them. That is something that's obviously very, very popular in Postgres. One problem, of course, with column encryption is where do you store the encryption key, right? Do you store it in a database server, right? Well, if you store the key in the database server, if somebody steals the server, they also get the key, right? So maybe that's not what you want to do. There is the concept of having some kind of cryptographic server in the middle, which can effectively serve keys to you, so you don't have to store them on the database itself. You can store the key on a client, in the client, or ideally, and again, this would be a case where you can encrypt, you can send a key across the network. Another idea would be to sort of encrypt the data before it goes across the network. So instead of sending the key with the data, encrypt the data on the client, then send it to the server. Then when the data comes back, you decrypt the data, right? So the server never sees the key, the server never sees the decrypted data, it just sees encrypted data. And finally, a great way of doing this is to have some kind of cryptographic hardware, like a security token that you can pull out of the client. So even if somebody steals the client and the server, if the key is not inserted at that time, you're safe. Now, the good news is that you can use this type of cryptographic hardware with Postgres. I have 4 security talks on my website. One of them is called one of them's called TLS encryption. It's basically with security it's basically called configuring security hardware and using security hardware. It has examples of how to sort of use these cryptographic hardware tokens, like a YubiKey is the one I'm most familiar with, where you can effectively sign the data with the YubiKey, send it across the network, get it back, and then decrypt it with the YubiKey. You pull the YubiKey out, there's no data. You can't even copy the key off the YubiKey. That's the beauty of the YubiKey versus a USB stick. The YubiKey, the data doesn't come out. If the private key of the YubiKey is locked into the YubiKey, you can't get it out. So it can't be copied. It's only on the YubiKey, right? And again, there's other hardware, cryptographic hardware as well, but that's the one I'm most familiar with. But I have examples in my blogs of using cryptographic hardware with Postgres. So if you want to kind of go in that direction, particularly for column-only encryption, I recommend you take a look there. So that does complete my talk. I'll be happy to take any questions. If not, it's been exciting to be speaking in person. Hello to everyone there on Zoom, and I hope you have a great rest of the conference.